Welcome back. So this is our last lecture on sort of standard distributions that you may or may not have seen anywhere else. So for this part of the lecture, we're going to talk about the beta distribution. Now, this is a waiting time distribution of a different nature to the ones we've seen previously. So suppose you've got sort of n deliveries, which you expect to arrive, expected in some time interval 0 to 1. We're just going to use 1. If your time interval is bigger, you can rescale units to make your time interval 0, 1. Okay? And, well, the probability that we're going to want to ask is, well, what is the probability that the rth delivery occurs in, say, a subset of 0, 1. Say this could be a small interval. So essentially, as a picture, you've got your time axis, say 0, 1. You've got some deliveries, and then you've got your set A, let's say it's this, and you want to know what's the probability that the rth delivery, in order from, like, ordered based on when they arrive, is going to lie in your time interval. Okay? And, well, we can actually, unlike what we did for the previous two waiting time distributions where we argue heuristically, this we can actually construct explicitly. So we're going to use a push forward to come up with the probability measure. So first of all, the space that we're going to work on is going to, we're going to take this to be the open unit interval with its restricted Borel sigma algebra. The reason we use open interval as opposed to closed doesn't matter. You could use the closed. We're going to find that the probability distribution we get doesn't attribute any probability to the endpoints here. So you can put them back in at the end and lose or gain nothing. Okay, so we're just going to use open because we can. Now, we're going to assume that there are n deliveries, and these deliveries arrive independently, in a sense that I'm not going to make super clear. But once we actually get to independence, you can come back and check that, yes, these are independent, deliveries are independent and uniformly distributed. So distributed like the uniform distribution on 0, 1. Okay. Well, a sample space we could have for the collection of n deliveries where we label them based on, so if we label deliveries 1 up to n, well then the sample space we would take for that is going to be 0, 1 to the n with its Borel sigma algebra. Now here, where we haven't ordered these deliveries, this is where, say we're expecting apples, bananas, and pears or something. The first one is going to be apples, the second is bananas, the third is pears. We're not... So this isn't the probability really that we're interested in up here, which is where we want whichever one arrives, say, third, where that may not always be apples. Okay? So here is one sample space where we just look at all of these things. We've labeled the deliveries independently, and we look at when each one arrives. Okay, but to map this to the sample space that we really care about, we should just select whichever one of these is the rth smallest for any way that they arrive. Okay, so, well, how do we write this? So we're going to have a t from, well, this, I'll call this set. Oh, and sorry, I left the probability measure out here. So we've assumed that they're uniform. So this is uniform 0, 1 to the n. Okay, so probability space rather than sample space. Now we've got a map from 0, 1 to the n to 0, 1. And this is going to be a bit hard to write it down explicitly, but what it does is t of sometimes t1, tn is rth smallest ti. Okay. And, well, you can check that this function is, well, between the two sample spaces we're considering. This is actually a random variable. It's measurable. And therefore we can use it to push forward the measure, but it is a little complicated to do so. So, well, let's just continue and try to figure it out. So I'll annotate this with some r and n because we want to keep track of these things. Okay, well, the push forward of u 0, 1 to the n under trn applied to some interval -infinity to c is going to be the same as the uniform on 0, 1 to the n of t r n less than or equal to c. Okay, and, well, this is the same as, yeah, no, let's just leave that as is now. So we're going to try to figure out what this set looks like. Okay, well, first of all, we can split. Let's leave that there. So the first thing to note is that we can split 0, 1 to the n into this disjoint union here. So I'll explain this in a moment. This is okay, so where these A sigma are the set of points of this form, okay, so just explaining this notation here. So sigma here is a permutation. So what that does is it swaps the n indices around. And then these sets A sigma are where once you've permuted these variables according to sigma, then you've got an increasing list of times. And then these are the sort of hyperplanes which have at least 2 of the times equal. So just as a picture to convince yourself, if we look at this when n is 2, then you've got badly drawn, you've got sort of a square like this for the 2 times. So say this is t1, t2 in these directions. Then this set here, there's only one of them, and that's going to be this diagonal line. And then when you don't permute anything, here you've got that t1 is less than t2. So this will be one of your a sigma 1, and this will be your other a sigma. Okay, and if you do this in higher dimensions, you're going to have these sort of higher dimensional triangles and planes cutting them up. And we pretty much throw out the planes because the uniform distribution is going to associate 0 probability to those. And then on these sets, we know the order. And that's going to allow us to figure out this. Okay. So let's keep going with our computation. Okay. Well, for one thing to note, before we continue, is that there are n factorial permutations in Sn, and the uniform distribution 0, 1 of n of each an, of each a sigma, is independent of sigma. Okay, and well, this is because the uniform distribution is invariant under this sort of reordering of the directions. Okay, and also the hyperplanes have probability 0, and therefore, in fact, these must all be equal to 1 on n factorial, because there are n factorial of them. They're all disjoint, and their union is all of 0, 1 to the n. Okay, so let's just continue with the computation then. Okay, well, for each different permutation we get here, that's going to exactly tell us what TRN is, because, well, then they're ordered from 1 to n. So it's going to be sigma of R, and because the volume of each of these sets doesn't depend on sigma, we can reduce this problem quite a lot, because you're going to just get exactly the same contribution from each a sigma n factorial times. So using that, we get u of 0, 1 to the n of t r n less than or equal to c is equal to n factorial times, well, the uniform distribution on just one of these triangles, 0, 1, n, t, r, n, less than or equal to c, intersect t1 dot 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 tn such that t1 is less than dot 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 less than tn. Okay, well, let's write this out as a big integral. I'll move that equal sign further back. So now we keep the n factorial, and the uniform distribution is just integration with respect to each coordinate. So we've got two conditions here. This is telling us that the rth largest one is less than or equal to c, and these are telling us that all of the coordinates are less than the next one. So we get a huge integral here. Okay, so first of all, we're going to have an indicator function that t1 less than t2 less than ... tn of t1 up to tn. Okay, we're going to have an indicator function that tr is less than or equal to c, because now these are in order, so the rth smallest one is really just tr of t1 ... tn d t1 ... d tn. Okay, and then we put all these conditions in for bounds on our integration, which is quite a mess. Okay, so let's just process that this is the right thing. So, sorry, I've got an alarm going off. First of all, we see that, well, t1, we are only integrating it up to t2, so yeah, t1 is less than t2. Likewise, for everything, all the indices less than r, say tr minus 1 is going up to tr, that's good. And then, well, tn is going from tn minus 1 to 1, and t all the way up to tr plus 1 is going from tr to 1, so that's all good, the order's preserved there, and tr is going from 0 to c. So yeah, we've correctly written down what should happen here. And then, well, you can explicitly figure out what this and this are by induction. I'm not going to do that. I'm going to skip to the punchline, which is what you end up with is this. So n factorial on n minus r factorial r minus 1 factorial integral from 0 to c of tr r minus 1 minus tr to the n minus r d tr. Okay, and we can just go through and relabel all the TRs. I'll just do that now so that we can recognize that this is actually telling us exactly what the density, well, for one thing, that this probability distribution does have a density and it's telling us what it is. So let's just relabel those as X. Okay, and just to recall what we were calculating here, this was the push forward via trn less than or equal to c okay, which is exactly what we would want the distribution. So this should really be the same as the distribution under TRN, the cumulative distribution function, sorry, evaluated at C. Okay, so there we've finished the problem, pretty much. So this distribution here is called the beta distribution. With parameters. Now this bit gets a little messy because we want to compare it to the beta function. So we say that it has parameters r and n minus r plus 1. Okay, and we write this as beta r n minus r plus 1. Okay, and well, the reason that we have this name is that this normalization factor, the reason is that the beta function, which is something due to Euler of r and n minus r plus 1, is exactly what we get as normalization. N minus r factorial r minus 1 factorial divided by n factorial. Okay, so this is Euler's beta function. Okay, and where we can give, like what we had for the gamma distribution, we're going to sort of just depart from what we were actually trying to model and allow these to be arbitrary real numbers. So the beta function has a different sort of, this Euler's beta function can be defined for any positive real numbers and is given by this 0, 1, s to the a minus 1, 1 minus s to the b minus 1 ds for a, b greater than 0. And therefore we can extend the beta distribution to have these other parameters, where what you would have then is the density. So in the notes this is clear, but this is like a bold-faced beta for the distribution, and the density itself, so what we integrate here, this part with this part, that would be the probability density, and that is going to, so if we put AB here, this has density non-boldface beta AB of S is equal to, well, if S is bigger than 0, it's what we had. So 1 on B AB of S to the A minus 1, 1 minus S to the B minus 1 for S. Well, really it's just S in 0, 1 and 0 otherwise. Okay, reasons you might want to change AB from being natural numbers, which, you know, our modeling technique, the story we've used to get here is really only taking these to be real integral numbers. If you're actually modeling something and you've got something that looks sort of like a beta distribution, then that's the reason that I assume that people would allow this A and B to be non-integer. Okay, well, that's the end of this lecture. So yep, we'll get on to our last standard distribution that we're going to see in the next lecture. So, yep, I'll talk to you then.